Go for it.
Good evening, everyone. Thank you for joining us. This is the first in a three-part series that I have up on the slide that I hope you can see. We're calling this the Oregon Coast Uncovered, and tonight we're going to cover coastal geology. Next week, same time, same place, we'll be covering coastal beach dynamics. That'll involve things like sediment transport and nearshore oceanography. And then we'll finish up on November 18th with an overview of the Columbia River Estuary. So, like I said, we're going to start with coastal geology tonight, and I'm going to start with the tectonics, coastal Oregon tectonics. And first, just a few words about the theory of plate tectonics and where it came from. Way back in the early 1900s, there was a German geophysicist, Alfred Wegener. He came up with an idea, and he called it continental drift. And what he did was he looked at a map, like the upper map that you're looking at here, and he saw that there were some good fits between continents. So, for instance, he saw that if you pushed Africa, it would fit right up into North America. And if you folded Central America up, it would fit up into the Gulf of Mexico. And if you pushed Africa back into Asia, there'd be a fit there. And actually, I remember doing this when I was like in 7th grade or something. I remember thinking, gee, it looks like there'd be a fit here. Anyway, so he put it all together, and he called his supercontinent Pangea, and he reconstructed those continents. He reconstructed all the continents with that in mind, and that's what you're looking at in the bottom slide of Alfred Wegener's reconstruction of the continents. And again, he called this continental drift. What he saw was, he was enough of a geologist and geophysicist to see that there was a good match between the geology of the African coast and the North American coast. The rock types were similar, the geologic structures were similar, and the same thing up between Europe and Scandinavia, British Isles, and Greenland. He saw a fit between the geology. So with this information, he got some confidence that, gee, maybe this reconstruction really worked. And these are the continents realigned according to Alfred Wegener. He also looked at paleoclimatic evidence. And what he saw was that around the world, in the upper part of the slide here, he saw that there was evidence of coal swamps in North America, in Europe, over in Asia, and in Africa. And he saw that with the present day configuration, these coal swamps shouldn't have been there. There shouldn't be coal swamps up in North America and up in Europe. And the way to justify that would be to reconstruct the continents so that the coal swamps were near the equator. And as you can see in that top slide, there's evidence of glacial ice on the equator. There's evidence of glacial ice in places where there shouldn't be glacial ice. And the way to justify that would be to reconstruct the continents so that the glacial ice was in Antarctica, was to the south, and that the coal swamps were aligned closer to the equator. So it wasn't just a fit that he was using some real geologic evidence here. He also saw a fossil, a similar fossil in both South America and Africa, when there wasn't any way that fossil could have gotten there. This was not a marine fossil, and there was no way to account for the fossils existing in South America and Africa without reconstructing the continent, so that organism could live in both continents simultaneously. And again, the way to do that is to push Africa next to South America. However, he published a couple papers arguing for continental drift but he got a lot of pushback, and the pushback had to do with the driving mechanism. Reviewers and other scientists just saw no way that the continents could have slid around and created a supercontinent. So his theory died for some years until the early 60s, when geologists and marine geologists went out and started taking transects across the ocean basins and doing more high-tech sort of geology and more geology to come up with with some further evidence, and that made them look more closely into what could have been driving these plates. And the mechanism they came up with was heat. And the model that's used is a convection cell. So here you see a simple convection cell where the water is on the bottom of this little kettle is being heated, and as the water heats, it rises. And as it rises, it moves laterally, and eventually it'll cool, and then that water will sink. And that is the model that was proposed, and that's the model that's presently used as a driving mechanism for the plates on the surface of the Earth. So heating deep down within the mantle causes molten rock material, molten magma, if you will, to rise. The magma rises. As it cools, it moves laterally, and then it drags the plate with it. And then eventually that'll cool, and then it will descend, pulling plates back down into the mantle. And I'll go into this in some detail. So just a kind of a broad overview of what I just said. If you look at the right part of the screen there, where my cursor is, if you look at the right part of the screen, you can see the yellow arrows are supposed to be showing mantle material rising up, cooling as it gets higher into the closer to the crust, the upper crust of the Earth. It cools, it moves laterally, and then it drags the upper crust with it. And that's just what we're seeing here. The white arrows are showing the, in this case, oceanic crust being dragged laterally by the underlying convection cells within the mantle. As the plate moves to the left, it eventually cools, and then it descends. And that's what we're seeing here. And that descending plate creates a trench on the surface, in this case, on the surface of the ocean. So once again, we have hot molten material rising from within the mantle. It cools, it spreads laterally, and it drags the upper crust with it. This is a reconstruction of what all the plates, all the major plates on the surface of the Earth look like today. Those numbers are the velocity of the movements of the plates, and they are in centimeters per year. So just as a rule of thumb, if somebody says, oh, how fast do plates move? I say a couple inches per year. And as it turns out, further support for the idea of plate tectonics is the correlation between earthquakes and the plate boundaries. And here, all the red dots are all the earthquakes that have occurred in the last, I don't know, 40 or 50 years, something like that. And if you go back and forth between this slide and this slide, you see a strong correlation. You see a 1-to-1 correlation between plate boundaries and earthquakes. And it shouldn't be any surprise, huh? So as two plates come together, there's going to be some disruption. There'll be an earthquake. And as plates subduct, there will also be earthquakes. All those little red dots in the middle of the oceans, so like all the little red dots in the middle of the Pacific and in the middle of the Atlantic Ocean, is something that I will cover in a few minutes. Another support for this whole idea of plate tectonics is the age of the rocks found on the surface of the Earth. And what we see here, the red stuff are young rocks, and the gray covered and yellow covered rocks are the oldest rocks. And what you see here is just what the theory of plate tectonics would predict. That is, that the youngest rocks are associated with plate margins. That's where the action is. That's where new crust is being created. And the stuff in the middle, so like in the middle of North America here, you see the Canadian Shield that has some of the oldest rocks found on Earth, 2.5 or 3 billion years old. And the reason that the rocks are so old in the middle of continents is that because they are away from plate margins. So these are old rocks that have been recycled over hundreds of millions and billions of years. And the oldest rocks, again, are found in the middle of plates where tectonically there's just not a lot going on. Eventually, those rocks will be subducted. They will be exposed. They will become part of a plate margin at some point, and they'll be subducted, and the cycle will continue forever. Okay, there are 3 major types of plate boundaries, and I'd like to go over these. Up top, we have a divergent plate margin where 2 plates are being spread apart. So you can see hot mantle material coming up from the interior of the Earth, spreading laterally and dragging the 2 plates away from each other. The middle model is a convergent plate margin where you have 2 plates colliding. And the argument is which plate is going to go under and which plate is going to go over. And as it turns out, oceanic crust is denser than continental crust. So the oceanic plate invariably is subducted. The oceanic crust subducts, and the overriding continental crust goes up. Continental crust is typically granitic or approximately granitic in composition, which is lighter, so it sits higher. And oceanic crust is typically basaltic with more heavy minerals, so it subducts, it goes under. The third type of plate margin is a transform fault where 2 plates slide by each other. So neither one of them goes under, neither one of them goes up, they just slide past each other. And I want to give real world examples of all 3 of these plate margins. And the first is a divergent plate margin. And the classic divergent plate margin is the Mid-Atlantic Ridge shown in this slide. The Mid-Atlantic Ridge is the longest mountain range on the Earth. It literally goes around. You can follow this around the whole Earth. And it stands thousands of meters above the sea floor. And this is where new crustal material is being formed, and the plates are being driven to the east and to the west. So the African plate is being pushed eastward, and the North American plate is being pushed westward. So the east coast of the United States is what we call a passive continental margin. There's no active tectonic activity going on there, whereas the west coast of the United States, that we're going to see in a few minutes, is called an active continental margin, which means that it is on a plate margin, and there are all kinds of things going on there, like earthquakes and volcanoes, etc. So once again, this is a real world example of a divergent plate margin. And this is just a little cartoon of the generation of a divergent boundary. So in the upper part, you see hot molten material spreading laterally, breaking apart the continental crust. So it's causing that much stress in the surface that it's actually pulling the plate apart. In the next part of the cartoon, you can see that that diverging is happening. So the 2 plates are spreading, and at some point, like what's happened in the Atlantic Ocean and like what's happening today in the Red Sea, that opening is filling with water. So once again, the crust in the middle, that blue stuff is oceanic crust. It's denser, it's sitting lower, therefore the world's ocean comes in and fills it up, and eventually, as we see in the bottom part of the slide, it turns into a full ocean basin. And this is an exact model of how the Atlantic Ocean formed. So it started off Africa and North America were stuck together. Upwelling of the mantle occurred, ripped the existing plate apart, created two other plates, and now we have the Mid-Atlantic Ridge. An interesting feature of the Mid-Atlantic Ridge is that, I'm going to go back a couple slides here. You can follow that. You can follow this right up into Iceland. Everybody see that? How the Mid-Atlantic Ridge goes all the way up into Iceland, and it is exposed. The Mid-Atlantic Ridge is exposed on the surface of Iceland real estate. That's what we're looking at here. This is the Mid-Atlantic Ridge exposed. And this is why Iceland's a tough place to live. If a few months ago they were having volcanic activity, earthquakes are not uncommon, but kind of interesting feature for people in Iceland to live literally right on the Mid-Atlantic Ridge. As I said before, the Atlantic Ocean is evidence of a mature spreading area, whereas the Red Sea is, if you will, the Atlantic Ocean forming today. So there is spreading occurring right through the Red Sea. It is a new ocean basin, and in some hundreds of thousands, millions of years, if the tectonics remain the same, the Red Sea will become a major ocean basin. And you can see going south of the Red Sea, those red lines showing rift valleys. If you're familiar with that part of Africa, it's really unusual geology. And that's what's shown down in the right-hand corner. There are rift zones right in Africa where spreading is occurring. So these are active rift valleys, and it's conceivable that someday the Red Sea will hook up with those rift valleys, and a new major ocean basin will form. I wanted to say a couple words about hydrothermal vents. Hydrothermal vents are a relatively new discovery, really since the 60s, when mostly Woods Hole developed submersibles that could go into deep water, where these hydrothermal vents discovered. And on the left-hand side, what we see a ridge crest. So we see a spreading center actually happening there. And there's what we call a black smoker forming, and that is just molten material coming out of the mantle, like we've already discussed. And as that hot molten stuff comes out, it is infused with seawater, and you get some really wild deposits. You get some really wild metal sulfide deposits that I can't go into much detail in this talk, but to the right, you can see one of those black smokers in action. So we're out here at 8,000 or 9,000 feet water depth, and you can see black molten material coming out of the interior of the Earth, mixing with salt water, creating some pretty wild deposits. And this is not a good photograph of a black smoker in action, creating some pretty wild formations on the sea floor. And there's another photograph again of these formations that form when the hot molten material cools, and this is what's left on the ocean floor. And studies of these have been the source of countless master's theses and Ph.D. theses of sailing ships over these features, putting claws down and recovering the rock, and again, the source of a lot of research. And just a little cartoon here. So here over in the left-hand corner, we see the Woods Hole submersible Alvin down having a look at these environments. Here we see a black smoker emitting molten material from the chimney. And the really interesting thing here is that we have creatures living down here at 8 and 10,000 feet water depth. So there's no light. There's no photosynthesis, yet we get tube worms that are huge. We get sea anemones, huge sea anemones, much bigger than we find on the beach today. Huge clams, huge crabs. So this is a really unique environment that's not being driven by photosynthesis. I'll get to what's driving it in a second. Host to some of the wildest life on Earth are associated with these hydrothermal vents. And it's been proposed that the origins of life formed at these mid-ocean ridges through a process called chemosynthesis. And chemosynthesis is simply a way of driving life-producing energy in the absence of sunlight. So there are some really unique chemical processes going on here that marine chemists feel could have driven early life. Okay, so much for a divergent plate margin. Let's have a look at a transform plate margin. And a transform plate margin is two plates sliding by each other. And probably the most famous transform fault is the San Andreas fault, where the Pacific plate is moving north, the North American plate is moving south, and someday Los Angeles will be a suburb of San Francisco. Convergent plate margins. This cartoon just shows the general mechanics of a convergent plate margin, and I'll go into some more detail in a second. But what we're seeing in the bottom of the slide are the convection cells, those heat-generated convection cells that we've been talking about. We have hot molten material coming to the surface. And if we look to the right, the convection cell is dragging geoceanic crust to the right. It's cooling, and then it's banging into continental crust that's sitting higher, and the oceanic crust is being subducted. And the same thing is happening to the left, but just with a little different geology. But I want to focus on the right for another minute here. So what happens as that crust is being dragged into the subsurface, it's reheating. And as it reheats, it is actually melting. And that's what we're seeing there. We're seeing the molten magma actually rising up through the crust, creating a volcano. So the subducting crust is uplifting the continental crust, causing a mountain range. And at the same time, the oceanic crust is melting. It's rising up through the crust, creating volcanoes. And if you live in Oregon, us who live in Oregon are intimate with this process. And that bottom part of the slide is showing the Juan de Fuca plate. The plate tectonics gets a little complicated off the coast of Oregon. It's not the Pacific plate, but it's a little remnant plate that they've called the Juan de Fuca plate. So it's not the Pacific plate that's being subducted under Washington and Oregon. It's the Juan de Fuca plate. Anyway, so here we see the Juan de Fuca plate is being subducted. It's oceanic crust, so it's going underneath the less dense continental crust. And as it subducts, it is heating. It is melting the mantle material. The mantle material is rising up, creating, in this case, the Cascade Mountain Range. And that's why, if you look at a map, the Cascades are a very linear feature. And it's linear because this process of subducting is, in this case, map-wise, it's a linear process, creating this line of volcanoes. So Mount Hood, St. Helens, Rainier, Mount Adams, etc., are all the product of this subducting plate. And in the upper part of the picture, you see good old Mount Hood there. It is a semi-active volcano. It could erupt any day. In fact, there are if you hike if you hike up high onto Mount Hood, you have to be careful of sulfur oxides coming out, and hikers have died by being trapped in essentially in an active volcano. Mount St. Helens, back in 1980 or so, was directly the result of this process. Okay, so far we've talked about what happens at a convergent margin when oceanic crust collides with continental crust. And like I said, the oceanic crust, it's denser, so it goes under, and the continental crust, being less dense, is pushed up. So that leaves us the question of what happens when continental crust bangs into continental crust. What happens? Neither body wants to go under, and what happens is both plates go up, and that's exactly what has happened to India. And here we see a little cartoon of India moving north, and the cartoon starts at about 70 million years, and eventually it bangs into the Asian plate. Both plates go up, creating the Himalayas. And it's still going up today, but erosion is approximately equal to the uplift. So the Himalayas today might be going up a little bit, but again, the erosion of the Himalayas are counterbalancing the tectonic uplift. Okay, we're going to shift gears here a little bit and have a look at Oregon coastal geology. The group I'm with, Oregon Shores Conservation Coalition, we are from Oregon, so I focus on the Oregon coast. So just very briefly, the Oregon coast looks something like this, where we have a broad continental shelf. It goes out 30 to 50 miles or so until it reaches the shelf break, which is a pretty steep break in the shelf. It then turns into the continental slope, which is a relatively steep feature, and then it flattens out to the continental rise, and eventually it flattens out into the abyssal plain, which offshore Oregon goes down to about 10,000 feet or so. So that's the general cartoon of what's going on offshore Oregon. We see continental crust sitting higher than the oceanic crust. And there's a pretty interesting feature that occurs off the Oregon coast, and that is submarine canyons occur. So a lot of sediment is being dumped on the shelf. That sediment becomes unstable, and it eventually, just by gravity, moves downslope, and it brings relatively shallow water sediments out into the deeper water. And that process is called a turbidity current. And I bring this up because there is a spectacular submarine canyon right off the coast of the Columbia River. And so this slide is showing, to the right, you see the Columbia River there. You see the Oregon coast. You see the continental shelf. And just offshore, just west of the continental shelf, just west of the Columbia River, is the Astoria Canyon, which is a spectacular feature along our shelf, and it has been the source of many of master's degrees and PhD theses. And that sediment eventually comes to a lot of sediment comes down the Columbia River. It has dug a big hole, creating the Astoria Canyon, and that sediment comes to rest as the Astoria Cone, which is a huge bathymetric feature right off the coast of Astoria. And this is a Google Earth shot of what I was just saying. It doesn't show it in a lot of detail, but it does delineate the Astoria Canyon very well. The cone isn't real well developed, again, due to just the nature of Google Earth. Okay, Oregon Oregon coastal geology is notoriously challenging. And rather than getting into the nuts and bolts of every little fault and fold and the rock sequences, I thought I would just present the big picture here. And you can come to Astoria and take my geology class, and we go into this in a lot more detail. But I just want to paint a broad picture of what's happening out there and why Oregon coastal geology is notoriously challenging. So what we see here is a reconstruction of the Oregon coast some tens of millions of years ago. So once upon a time, there were microcontinents off our coast. There were island arcs off of our coast. And this is true for Washington and a lot of California too. And over time, due to plate movement, due to the Pacific plate movement, the Pacific plate is being subducted under the trench that we see there. And over time, that island arc is eventually subducted. You see that? So we have our island arc moving to the east underneath Oregon. But what happens is, as the oceanic crust is being subducted, the island arc is being scraped off onto Oregon's coast. So that's what we're seeing here, the accretion of the island arc onto the continent. And this continues to happen, and eventually our microcontinent will be scraped off. And you can just imagine the complicated geology that this is creating. So if you're a geologist, or if you know geology and you're used to layer cake geology like we have in Iowa, in the middle of the continent, where you just have rock layers sitting on top of rock layers, here we have massive deposits of rock being scraped off the subducting plate and being plastered onto Oregon's coast. So again, I just want to present a broad picture here of why Oregon geology is notoriously difficult. And here's a photo from Short Sands, and you can see to the east, to the right, you can see that the whole area has been uplifted. There's evidence of faulting in there. There's a big slump right in the middle. That's recent stuff. But yeah, it's a geologic challenge or a geologic nightmare, depending on what kind of geologist you are. And some more coastal geology, where you see a series here of faults and folds, again, making the geology really challenging. This tectonic activity not only makes the geology interesting and challenging, but it also has wreaked havoc on people who want to live along the coast. And this is a landslide map from Oregon's Department of Geology. It's called a slide. It's from their Slido website. And all this is Astoria, by the way. We're looking at this is a map of downtown Astoria, and all that brown is evidence of past slides. So there's been slides all over Astoria. You have to be careful of where you buy and build in Astoria, and not just Astoria, along the whole coast. But I live in Astoria, so I'm most familiar with Astoria geology. It can be a challenging place to live. As you can see here on Duane and Fifth, there's a huge landslide here. Luckily, no houses were involved. However, back in 21 on Alameda Avenue, there was a slide from behind the house. It pushed the house off its foundation and just about into the street. And you can see here's the same house. That green trimmed house on the right is the house that I just showed you. And if you look behind the house, you can see what caused it. That hill became oversteepened, and the whole thing just caved in, pushing the house off its foundation. And that gray house up top would not be a good piece of real estate for someone to own. Okay, as promised, I pointed out to you some features in the middle of plates. I pointed out to you volcanic activity, volcanoes, submarine volcanoes in the middle of plates that didn't conform to the plate tectonic model. And I want to take a few minutes to talk about this, because this is interesting stuff. So here we have our map once again showing the major plate boundaries. And in the middle of those plates, we see red dots that designate volcanic activity. And again, the plate tectonic model doesn't seem to explain why you would have volcanic activity in the middle of a plate. Well, this is where the theory of hotspots has come in. And what happens is, what causes those volcanoes in the middle of plates is shown in this little cartoon. So here we have a mantle plume. So we have a hot mantle plume. It is an anomaly. It's just a hot spot in the middle of a plate. It is a geophysical anomaly, and it's hot, and it's spewing up hot magmatic material. And as the plate moves over it, and we can see in the red arrow there, we can see the direction of the plate movement. In this case, this is the Pacific plate. As that plate moves over that hot spot, it creates an active volcano, just as we see in Hawaii today. However, as the movement continues, the volcanic activity stops, and we end up with these island chains that you see all over the Pacific Ocean. And if you look at the bottom part of the figure, we see Hawaii that is presently under a mantle plume, and you can see evidence of plate movement there to the left, to the west. And then you can see a sharp change in direction of plate movement right here, indicating a change in plate movement direction. So really an interesting feature, and this couldn't have been explained without the knowledge, without the theory of plate tectonics. And here's a close-up of what I just said. So the Hawaii is active. There's a Hawaiian chain. Those islands used to be over the hot spot, but they moved away. And then there, like 48 million years ago, there's evidence of a major shift in plate motion, creating the seamount, the Emperor Seamount chain. A side effect of this is the creation of an atoll. And the Pacific and the Indian Oceans are filled with atolls. And how a lot of people have heard of atolls is we tested nuclear bombs in different Pacific atolls. Anyway, how they formed is by the creation first of a volcano. So that's what we're seeing to the left there. And as the volcano erupted above sea level, so as a submarine volcano erupted, it built up above sea level. And as it came above sea level, corals formed. So all corals really need is a nice, clean, warm water and some jump starting biologic material, and you can create a fringing reef. And that's what we see in the bottom part. We see the fringing reef sticking up above sea level. In the middle part of the cartoon, we see that the volcano is no longer active. It's being weathered. It's being eroded down, but the reef is continuing to grow. And if you look at the bottom part there, you see a more established barrier reef. And with time, the volcano will be eroded completely below sea level, and all you will be left with is the atoll and a lagoon surrounded by the atoll. So this is the geologic process for creating all those cool atolls and lagoons that we have all over the Pacific. Okay, what is the predominant Oregon coastal rock type? It is basalt. Basalt is everywhere. It's hard to get away from the basalt when you're walking down the Oregon coast. And I'm going to hold you in suspense. So where does all the basalt come from? You're going to have to come back next session to see. And That's all I have to say.
All right, thanks so much, Ed. I learned a lot. We already have one question in the Q&A box. Thank you to Ashley. If anybody else has any questions, please feel free to add them in while Ed is answering this one. Ed, our first question from Ashley is, how deep is the Astoria Canyon?
The Astoria Canyon starts at just a couple 100 feet water depth and goes down to a couple 1,000 feet water depth.
Wow, that is quite deep. Does anybody else have any questions? I know you left us on a cliffhanger. I'm excited to learn more next week.
That's to entice everybody back. I know everybody's going to want to know where that basalt
We
comes from.
gotta know. All right. Well, I'm not seeing any more questions coming in. Now's your chance, everybody.
I want to thank everybody for their attention. And like I said, next week, we're going to get into coastal oceanography. So we're going to move away from geology and look at the coastal oceanography.
All right, Ed, we do have one more question here. This question is from Mark. Mark asks, with new research suggesting that the Cascadia Fault is segmented, do you have a feeling if certain areas are more tsunami prone than others?
You bet. Yeah, there was just a 6.0 off of Bandon, that's
Wow.
in Southern Oregon, and it created no earthquakes. It created no tsunamis. And so that is strong evidence that the fault plane is segmented, so you can
Mhm.
have movement along the fault plane without the whole fault plane moving. So good
Yeah.
question. Thank you.
Great question, Mark.
Yeah,
That's very interesting. We're
good
getting
question.
a lot of appreciation in the chat, which we love to see. I thought that was great, so I'm glad everybody else enjoyed it too. Let's see, last call for questions. Anybody? All right, it doesn't look like it. Well, thank you everybody for tuning in. Ed, anything you want to part with?
Nope, that's it.
All right.
Oceanography next week.
Next week. And if you have anybody that you think would really enjoy this and maybe they didn't quite register in time for this one, I'll be sending the recording out to you all in the next day or so, and encourage anybody else to sign up for the next two. And we look forward to seeing you all next week. Bye, everyone.
Bye-bye.